Okay, so in this video, finally we are ready to define what is orthonormal basis for in a separable Hilbert space, and we're gonna work with Fourier series. Okay, so so let me start with a definition. So definition this is a common term. So a Hilbert space H is said to be separable when there exists a countable dense subset of H. Okay, it sounds scary, but you'll see it's very easy to give you an example. So example, let's say before discussing this, let's go on example. So let H, the Hilbert space, be the real numbers, because the real numbers we have an inner product in the real numbers. Okay. There exists a countable dense subset. So what subset of the real numbers you know that is countable? Countable means 1, 2, 3, 4, 5, 6, 7, 8, 9, those, right? So you know the natural numbers, the integers numbers. Turns out the rational numbers are also countable. When I teach math proofs in undergraduate, I always teach this. If you are interested, so go to my office hours. I will show you a very beautiful proof of why we can count like 1, 2, 3, the rational numbers. There is a nice way to count the rational numbers. Okay, so it's countable. And what does it mean to be dense? Means that if you take a real number, okay, so x real number, there exists a sequence of rational numbers. There is a sequence of rational numbers. There is a sequence, let's say q sub n, and all these guys are rational numbers, such that the limit of q sub n when n goes to infinity gives you x. Okay, so that's possible. So for example, you take a square root of 2. So there is a limit of rational numbers converging to square root of 2. The same thing for exponential and so on. Okay, so that's what it means to be dense. So Q is dense. So sometimes you say, another way to say that is the closure of the rational numbers is the real numbers. Yeah, the closure of the rational numbers is the real numbers. Okay. And that's notation, but you took analysis and you are the master. You understand you have to take analysis. So it's good that you start getting used to this notation and these words, and you know, it's just a matter of getting used to get the terms, right? I'm gonna assign you some homework leading with limits of sequences and functions. That's what we really need. Okay. And but that's, you know, I'm gonna give you time to complete that homework. You probably thanks to that homework I might be able to meet a lot of you. So there's nothing to be scared, but you know, it's something that is coming. Okay, so we know what is separable. Now we do finally we're gonna define what is an orthonormal basis for a Hilbert space. So say definition. An orthonormal basis in a separable Hilbert space H is a sequence is a sequence WK k bigger or equal than 1 subset of H such that, so remember, so Hilbert space is an infinite set. Okay, so you need, that's why you need more than infinite set is an infinitely dimensional set. Okay, so R3 is 3 dimensions, right? R2 is 2 dimensions and R is 1 dimension. Okay, Hilbert spaces, the dimension is infinity dimension. Okay, infinite dimensional. So that's you know, that's why if partial differential equation is interesting, because we work on infinitely dimensional. Why? Because we're working with functions. These are functions. Okay, our elements are functions, so not points, are functions. So we had 1 function, 2 functions, 3 functions, so on. So so we want to see when these paths are converging to. Okay, so you have infinite convergence. Instead of having a sequence of numbers, you have a sequence of functions. So that's what is helps to the infinite dimensional thing. So we have the conditions. So to have an orthonormal basis for a Hilbert space, we need first that let's say, instead of the WK, let me use UK. Sorry, let me use UK since I was using U on my previous talk. So let me keep using my U. Okay. So I'm gonna say UK inner product with UJ equals delta KJ, and K and J are bigger or equal than 1. And the inner product of UK is equals to 1. This is if is orthonormal, means orthogonal and normal. So this is orthogonal and normal because the inner product is gonna give you of itself is gonna give you 1. Okay, it's just a nice thing, but with orthogonal is good enough, but you can normalize it. And so this is part 1, right? Such that 1 and then 2, and every x in the Hilbert space might be expanded in the form. So we already know that, right? Because we said that in my last talk, we said that this is the alpha 1, right? And I want to express x equals alpha 1 plus u1, alpha 1, that is a number, times u1, that is the vector, plus alpha 2 u2. So let me write it like this. This can be written as 1 alpha 1 times u1 plus alpha 2 times u2 plus alpha 3 u3, right? So you understand, right? But in another way to write this, I can write just sum of combination, right? Alpha I ui, right? I equals 1 to infinity. Yes, right. So so I if I repeat my trick, over here, remember I said x equals alpha 1 times u1, alpha 2 times u2, and so on, but I want to know what is alpha 1. So in order to do alpha 1, I did the inner product of x with u1, and I got this. So actually alpha 1 is x inner product u1 over inner product u1 with u1. So I can write this, guys, as actually this is sum of I equals 1 to infinity of ui, but I said this is the inner product of x ui divided by ui comma ui, right? But further is normal, right? That means ui with ui is 1. You see here, ui with ui is 1. So actually I have a very nice formula. It's beautiful formula. It says x comma ui is ui. Okay, so this series, so this formula, so in conclusion I had this formula. So the formula x equals sum of I equals 1 to infinity of x comma ui inner product ui is called generalized Fourier series. So we're gonna see next examples of Fourier series. We're gonna call it sine Fourier series, cosine Fourier series, and full Fourier series. So what all that I'm gonna do for to be the sine series, I need to do the ui's, they have to be sines. For cosine series, the ui's has to be cosine, and so on. Okay, so that's uh, the philosophy here, and the numbers, because these are numbers, and the numbers, let's call it alpha k equals x comma ui are the Fourier coefficients. Of x with respect to the basis ui I bigger or equal than 1. Okay, so the lesson here is, first you find an orthogonal set. So you're gonna find a set of functions that are orthogonal between each other. Okay, and that's your homework. You see your homework, and we see already here an example. I put here, I prove it for cosines, right? So this is gonna be the cosine. This is gonna make my cosine series. Okay, so I already proved this is orthogonal, and if I do the product by itself, I'm gonna get square root of 2 pi, right? And then this is saying that this is a orthogonal cosine set between minus pi and pi. So okay, so that's orthogonal. That's this is the cosine set, orthonormal set between minus pi and pi. and we are gonna make Fourier series around that. So you will see it clearly later. Well, in a second, what is this all about? Okay. So this is uh, the 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 Fourier series like definition. Okay, so let me give you some examples, and then we're gonna talk about convergence after I do some examples. Okay, because that's I think it's time for you guys to calculate. So with this you can do your homework. So it's time to get like more specific, right? I have been taking this approach uh, of going through the general definitions, and now we're gonna get big on specifics. So let's call, uh, let's say we're gonna do Fourier series. Fourier sine series. Okay. So if we consider Fourier sine series, so you wanna do Fourier? Let's do Fourier cosine series because I have it on the top. Okay. So Fourier cosine series. Okay. So let's consider the set of functions. So we're gonna consider the set of functions as follows. So let me follow this notation. I want to make sure I use this notation to be consistent with at least with one book. So I want to use so let's say consider the set of functions, and we're gonna say one. We're gonna consider one. Okay, what did I consider here on the top? So yeah, I consider 1 cosine of x, cosine 2x. That's what we're gonna consider. Okay. So 1 cosine of x, cosine of 2x, cosine of 3x, and so on, cosine of 4x, and so on. Okay. So you wanna consider that set, but if we already did this, okay? So so you could write this as, you could call this set of the following way: cosine, and let's say nx, right, from n equals 0 to infinity, right? So in this sense, this is these are your, well, let me call it I, so it's consistent with my other notation. I don't like it very much. No, I don't like it because it sounds like complex. But this is basically your u should ends, n equals 0 to infinity. Okay. So that's supposed to be your orthogonal set, right? So we already proved that the integral, or if you want, the inner product of cosine of nx with cosine of mx is equal to 0 if m is different of n, right? Therefore, it is an orthogonal set. Okay, it's orthogonal. But let's say that I'm gonna do last time I did it between minus pi and pi, right? I did this one between minus pi and pi. So this time I'm gonna do it between 0 and L. So for the definition, so let's consider the set of functions in the interval in 0 L. Okay, so we're considering between 0 and L, we're considering all these functions. Okay, so we're gonna have to make a change if I'm doing, if I consider it between 0 and L, I had to make some changes. I had to make, I make it 1, and then I'm gonna call it because I want to do it for in general for any zero interval 0 else. Okay, so it's useful for you guys in general for any interval. Otherwise, you guys have to do this every time. So here, because I'm between 0 and L, I'm gonna consider these guys divided by L. Why? Because I'm gonna have they're gonna be well, the formulas are gonna follow. Okay, so it's a way to do it. Okay, so I could choose to do it different, but that's the way I'm gonna follow. That's what I want to make sure I follow my my book. But my book, yeah, my book wanna do it. Okay, so my book wanna put also m pi x. So okay, so we're gonna do we're gonna put pi, and we're gonna put pi. Okay, so we're doing in general. Okay, so this is better for my formulas. Okay, so I'm doing in general. Okay, so let me erase this guy. Okay. So this guy should be n pi x l. You will understand later why I'm making your life easier when I consider it like this. L, little l. Okay. I'm making it orthogonal, right? And this, this formula will follow the same way. So m pi x over L is over L. Actually, for that's what I needed to. I need that pi because I'm making for 0L, right? So on the other one, notice that I conveniently choose minus pi and pi, my interval. Okay, my interval was minus pi and pi. You see, because when I integrate between minus pi and pi, these guys are gonna cancel when I plug in pi. If I'm doing any L, 0L, so let me show you here really fast. If I'm doing 0L and I'm gonna do the integral, right? So I need those guys to cancel, right? So integral between 0 and L. So let me put it like this: the inner product of cosine n pi x over L, inner product n pi x over L cosine n pi x over L is going to be the integral between 0 and L of cosine n pi x over L times cosine n pi x over L dx. Okay, And then I do the similar trick I did before. And this is gonna be 0 if m is different of n. Okay, so because I need that pi there, so when I plug in, this L cancel with this. When I plug in the L is gonna cancel with the L, and the n pi and m pi is gonna make the magic. Okay, they're gonna cancel, just like they did over here in my last example over here, when I did it very specific. When I did this integral, you see, I have to replace like this. So you just put mx pi cosine nx pi. You factor the pi and just keep working. Okay, and it's just gonna be the same thing. Okay, so this is gonna be 0. This is gonna be 0, so they are orthogonal. Now, if you do the let's say you wanna know the inner product of the norm. So you wanna know what is the cosine of, let's say, m pi xl with itself, because you wanna normalize it. You wanna have 1 on it. Okay. So if you do this integral, you will get you will get the following. This integral between 0 and L equals cosine times cosine is cosine square n pi x over L dx, and then this is gonna give you 1/2 over L. Okay, so this is basically the norm of cosine square n pi x over L right? So we have to, well, that will be the norm square, right? So when we wanna make it unitary, so we need to divide by one of these terms to make it normal. Okay, but I think I'm just going a little ahead of myself here. So let me see. So that will be the cosine. Okay, so similar, you'll get the sine series. Okay, instead of considering cosines, you'll define it using sines. Okay, so let's define it like this. So definition. So it's kind of we have a whole once you have the orthogonal set, you can just define the cosine series, okay, or whatever series you want. So let's say definition. The cosine series, on 0L for let's say for phi of x is given by the following. So you can write the function. You want to approximate the cosine series. You can approximate a function using cosine series. So this is what you have to do. This is gonna 1/2 of a0 plus sum of n equals 1 to infinity a sub n cosine of n pi x over L. Okay. Now, so how can you find a sub n? Okay, so actually you already know, because what you need to do is to find the inner product of this guy. Okay, so you want to know, let's see, so let me do it again. So let's say we want to find a sub n, right? So what is, so let's go back here. So example, well, okay, I'm gonna, before writing the formula, okay, let me write the formula and then I'm gonna explain to you what is the formula coming from. I think you already have an idea. So a sub m, where a sub m equals 2 over L integral between 0 and L phi of x cosine m pi x over L dx. Okay, so where is this coming from? Where is that coming from? So we do the same trick. So let's say how to find, so example, or let's say remark, let's find a sub n. Let's find the a sub n. Oh, let's find the expression for a sub n. So how do I do it? So last time what I said is this is u sub n and this is a sub n, right? So I need to find an expression. So I do the inner product of phi of x with cosine n pi x over L, because I want to see what happens, right? So I'm going to do the whole inner product. But when I do the whole inner product, I have 1/2 a0. No, sorry. This is, oh no, that's fine. Plus the sum of n equals 1 to infinity a sub n cosine n pi x over L, comma, and then cosine n pi x over L. So we already proved that, so I can take the one with the cosine n pi xl is 0, right? Plus the inner product of the sum of these guys. Well, okay, let me do it slowly. So this is gonna be equals to, I can take the half and the a0 out. 1/2 of a0 and 1 comma cosine n pi x over L, then plus, and now, but this is properties of the inner product. This is a plus b, this is a plus b inner product something. So I just split it, right? And I factor in here the 1 and the 1/2 a0. Now I have inner product sum of n equals 1 to infinity let's take the a sub n cosine m pi x over L, comma cosine m pi x over L. And now out of this inner product, okay, out of this inner product, all they are orthogonal except the one that is the same. So the only alive is m, because it will be times 1. Cosine m pi x L times, in the inner product, cosine m pi x over L, inner product cosine m pi x over L is going to be 1. All the others are going to be 0. Now this guy, let's assume m is different of 0. Yeah, so if n is different of 0, then this is not 1, so this will be orthogonal. So let's say m different of 0, just to do on the general case, okay? And then I have this guy, so I have this will be 0. So phi x, so I need to find a sub m is gonna be part of, okay, sorry, this is not 1. This is not 1 yet, sorry. This is not 1 yet because I didn't normalize it. So this is inner product of cosine m pi x over L, comma cosine m pi x over L. Okay, this is not normalized, so this is not 1. Okay, because I didn't normalize it. Okay, so this is and then I have here phi of x times this guy, right? But now, but I have an expression for this. Okay, so well, let me put it here. So m times this guy. So there is a formula for this. Am, this is the integral between 0 and L. So, okay, let me put it. Integral between 0 and L, cosine m pi x over L, cosine m pi x over L dx, right? So there is a formula for that, so you can use your integration formulas. This is just cosine squared, right? So you have formulas for that. This is am, and this will be 1/2 L. So you can just verify that, okay? So in conclusion, this phi x cosine m pi x over L is am 1/2 over L, okay? So that's my conclusion. So this guy is really phi of x cosine m pi x over L is this guy. So what I'm saying is, well, or better, this guy is the integral between 0 and L of phi of x cosine, sorry, 0 L phi of x cosine m pi x over L dx, right? So in conclusion, I have the following expression. So am equals the 2 is dividing, is going to multiply, the L is multiplying, is going to divide, integral between 0 and L phi of x times cosine m pi x over L dx, okay? And thus the formula we have over here. Okay, so what I'm saying, I'm sorry I have taken so long to do this. I follow several books, so it's hard to keep notations. I'm trying to put in the most unified way. So you have an orthogonal set. In this case, we are working. Let's go back. Our orthogonal set is cosine x pi over L, cosine 2 pi x over L, and so on. Why we choose that? Because we are between 0 and L, so it's better to put the pi there. Okay. So we verify it's orthogonal. So if you don't believe me, just go do the job. But then, since I have my orthogonal set, I define the cosine series. So what I'm saying is that you give me any function, for example, f of x equals x between 0 and L. And I'm gonna find you a series, a sum of series, such that that sum is gonna converge to this line very nicely. Okay? So basically, that's what is an infinite sum. So you give me any function, continuous function, in an interval, and I'm gonna find you an approximation to that function. Okay, that's kind of half of the story, because it's gonna have to be periodic. So pretty much this is saying that I'm doing the same that Taylor's theorem was doing. Okay, so as I said, our purpose is this is Taylor's theorem, and I need somebody to volunteer to talk about Taylor's theorem. This is calculus 1, calculus 2, and I want to just talk about Taylor's theorem and the convergence of Taylor's theorem. Okay, so what we're doing is, instead of finding this infinite sum, we are finding, instead of using polynomials x minus a squared and so on, we are using cosines. Okay, so that's why this is that good. Okay, this is really good stuff right here. Okay, and so from now on, what we're gonna do is just use this definition. Okay, so I could just give you this definition and forget everything about it, but you're a graduate student, so you have to suffer a little bit, sorry, to see this in detail. So this definition is what we are gonna use for the exercises. You can start now your homework. So now I'm gonna do the same. I'm gonna define sine and full Fourier series, but in this case I'm not gonna go over all the details because it's similar thing. So I'm gonna skip that. But now I can give you, with peace of mind, I can give you the definition. So I'm gonna give you the definition of sine series. So for my definition of Fourier or sine series, so definition of Fourier sine series. I apologize if you know French, because I'm not pronouncing Fourier correctly. So the Fourier sine series is defined by the Fourier sine series for phi of x. Okay, for a function phi of x is defined as phi of x equals the sum of n equals 1 to infinity a sub n sine n pi x over L in the interval 0 L. Okay, and where a sub n is where a sub n is equals to 2 over L integral between 0 and L phi of x sine of n pi x over L dx. Okay, and now I have to define the full Fourier series. Okay, so we have sine Fourier series, full Fourier series. Okay, and then here we go, definition of the full Fourier series. So the full Fourier series, and so I should say that this is not really in Salsa's book. Okay, Sandro Salsa's book is no, he doesn't really do too much on Fourier series. So what happens, and you're gonna love it, because when you're starting solving the partial differential equation, the partial differential equation is gonna give you two ordinary differential equations. One of those ordinary differential equations is gonna generate a Fourier series. Okay, so this is how everything starts connecting in a beautiful way. So the full Fourier series or simply the Fourier series. When people talk about Fourier series, this is the one that they're talking about. Okay, you have to be specific if you are talking about sine or cosine Fourier series, but this is the Fourier series basically of phi of x on the interval minus L. So notice here, this is in an interval minus L. It has to be symmetric. The full Fourier series, it has to be symmetric. So let me make you hear some warning here. So that means be careful, right? But in Spanish means I. So watch out, okay? So ojo in Spanish. So watch out with that. Is defined as phi of x equals 1/2 of a0 plus sum of n equals 1 to infinity an cosine n pi x over L plus bn sine n pi x over L. Okay, so what are we saying here? So in Fourier sine series, my orthogonal set is gonna be sine, right? Sine pi x over L, sine 2 pi x over L, sine 3 pi x over L, and so on. Over here in full Fourier series, my basis is gonna be 1 cosine pi x over L, cosine 2 pi x over L, cosine 3 pi x over L, so on, and sine pi x over L, sine 2 pi x over L, and so on. Okay, so this is so let's put these warnings. So warning. Okay, so let's put here warning. The interval is twice as long and the eigenfunctions now are all the functions one cosine n pi xl sine n pi xl where n equals 1, 2, 3, and so on. And the formulas are the following. So a sub n is 1 over L, in this case is 1 over L, integral between minus L and L, phi x cosine n pi x over L dx. This is n equals 0, 1, 2, and so on. And then b sub n, this is 1 over L, integral between minus L and L, phi of x sine of n pi x over L dx, and this starts in n equals 1, 2, 3, and so on. So b sub n start in n equals 1 and a sub n starts at 0. So b sub n's are with the signs, okay? So, and we take basically the a0, the one that is coming with a0 is cosine of 0, so that's 1, right? So a0 corresponds to 1, okay? Okay, guys, so I think this is enough for definitions, and now we're gonna start doing the examples. So this part you're gonna understand and enjoy better, because we're gonna do calculations. Okay, so I hope you understand the connection, and you know, so for an undergraduate student, we usually just tell them, this is the series, find a sub n and b sub n, and they just find the integrals. But we have been all the way of bases, linear algebra, Hilbert spaces, inner product, because we're gonna see some real convergence. Okay, so we're gonna stop here the video.